starting.
Ok.
Certo? Aí faz só last call. Acabei de mandar para o pessoal da CMD, mas... É. Giovanni, if you can share your slides, please. We're going to start at 10:02. Okay, 2 minutes delay. If you can share the slides, it'll be good, and you'll help later on because we are closer. Okay, great. Professor Lucia here to support her diamond boy.
All right, everyone can see my presentation?
Yes, we can see.
All right.
Just a second, everyone is joining now quite fast now.
All right.
We can start at 10:02, but then we have about 5 minutes.
Okay.
Okay, just give a time for everyone to start. Yeah, it's getting momentum now, the numbers now. That's good.
Bom dia.
Yes, bom dia. Rafael Nagal. Okay, it's getting momentum. Okay, just for those ones that are just arriving now, we're going to start 10:02. Okay, just to give 2 minutes for everyone to adjust their microphone. Good morning, everyone. How feel? Good morning, Lucia. Good morning, Cauê.
Good morning, all.
Good morning.
This.
Okay, welcome. See what's going on. Papa Sandra, good morning. Okay, I think, okay, good morning for everyone. Okay, first, thankful everyone to be here together. We restart the CINE Talks at CINE, and now we have a different approach that the CINE Talks will happen every 2 weeks and our speakers are the postdocs from CINE, the postdoc researchers. CINE counts today with a larger number of postdocs, is about near now to 70 postdocs, including all the programs. Means they constitute the main pillar of CINE today for research, those ones that are put their hands on the laboratories, computation simulations, machine learning applications, so on. And then they maybe today are the best ones to provide for us and to make the interaction between all the programs, and beyond of that, to tell for everyone in CINE and beyond of that, what we are doing the best. And then we have a large number of volunteers that we started CINE Talks this year, and then we have to select those ones that we start, because as you say, for every 2 weeks, we don't have too many slots, and then we, as a volunteer, the Dyovani Coelho put himself in the position to open the CINE Talks. It's an honor for us that he put himself. And the history of Dyovani Coelho, he started here at the São Carlos Institute of Chemistry, doing the PhD, Professor Sergio Machado, worked with, as a postdoc with Professor Ernesto Pereira, and also Lucia Mascaro in the last years. And then he's with us since the first phase of CINE for several years already. He has one of the postdocs that understand most of the things that what does it mean CINE for us. And then, of course, it's an honor for us to start the CINE Talks with him. Dyovani, it's a pleasure for us, for everyone here, to have you to open the CINE Talks for us. Professor Ana Flávia Nogueira, our director, is here present just to honor you and to, at the final, maybe we have several questions too. All your colleagues and friends and faculty members are here present to say enjoy what you are going to tell for us. Now the stage belongs to you, and thank you very much to accept our invitation for that.
Thank you very much for the kind introduction. I am Dyovani Coelho, and today I am in charge of this talk. So first of all, thanks for the CINE Hub for this opportunity. And this is my email. Everyone can feel free to contact me if you have some questions or some collaboration ideas and things like that. So I'm part of the Federal University of São Carlos, more specifically the Center for Development of Functional Materials and the Center for Innovation on New Energies, the CINE. So thank you very much for the opportunity. Today I will talk a little about my career, more specifically my career in the CINE and my research inside the CINE. I will start with motivations, why to study the catalyst degradation with sensitive techniques, why we need to use really sensitive techniques to study catalyst degradation in situ or online. That will be the examples that I will show for you. The methods used here, how was it done, how to do the catalyst electroposition, and how to study the catalyst degradation. And more interesting, the activity stability behavior of the cobalt, nickel, iron, phosphorus alloys, which is the main topic here, discussed here today. And the highlights, how to minimize the catalyst solution. So let's start with my academic career. I start my undergraduate at chemistry in Ponta Grossa State University in 2004. Then I moved to São Carlos Institute of Chemistry in 2009 to do my master and PhD degree under supervision of the Professor Sergio Machado. Then I moved to Federal University of São Carlos in 2015, where I did my postdoc research under supervision of Professor Dra. Lucia Mascaro. And then I have a little break to do my research internship in 2022 in the Helmholtz Institute Erlangen-Nürnberg for Renewable Energy to do this work that I will show for you here today under supervision of the Serhiy Cherevko, Dr. Serhiy Cherevko. And then I back into the Federal University. As you can see here, I have a lot of experience in electrochemistry because I start my undergraduate, I start my scientific research using the techniques based on electrochemistry, so I have a lot of experience in that. But I have experience too in the overviews, characterizations, and transition absorption spectroscopy, Raman spectroscopy, XRD diffraction, AFM, optical microscopy, scanning electron microscopy, transmission electron microscopy, and of course, techniques used to produce thin films like layer by layer, spray coating, drop casting, spin coating, electrodeposition, of course, and the hydrothermal deposition too. Let's start talking about the CINE. The CINE is the Center for Innovation of New Technology. It was created by the FAPESP and Shell in association with consolidated laboratories of 5 traditional universities from the state of São Paulo here in Brazil. And it was created to promote the energy transition throughout the research laboratories, for the prototypes, and even for startups and things like that. So it's more or less like how to use the knowledge here inside laboratories to produce prototypes to society in general, to produce knowledge and economic issues and things like that. Inside the CINE, we have 4 divisions. So the first one is energy generation, which is based on the solar panels and the wind power. The computational materials design, the CMD, the AES2, the advanced energy storage 2, and the green hydrogen, which is one of that I am part of. So here you have the website where you can take more information about the CINE and the research divisions and the project inside the research divisions. Today I will focus on the green hydrogen, who is responsible for, as a principal investigation, the Professor Ernesto Pereira. He is responsible for the project 1, 2, inside the green hydrogen research division. And this project is entitled New Electronic Materials for Water Deposition in PEM Electrolyzers. And we have another one project, which is the green hydrogen generation from electrolysis and photoelectrolysis, new catalyst, membranes, and scalable. Who is in charge of this program? This project is the Professor Dra. Lucia Mascaro, who is the co-principal investigator of the green hydrogen research division. And these projects are a little different from each other. Of course, the first one, the project 1, is focused on the catalyst based on iridium for PEM electrolyzers. So here, the main goal is decreasing the iridium content in PEM water electrolyzer, which today is the main problem of this kind of technology, is how to decrease the amount of this catalyst that is really expensive to use in PEM. The project 2 is another focus, is focused on the hydrogen from photoelectrolysis and electrolysis in alkaline media. So here, the project 1 is focused on PEM water electrolyzers, and the project 2 is researching things to produce AEM electrolytes, anion exchange membrane electrolytes. And here, of course, we are focusing on everything that is that produced in the device of AEM and water electrolytes. But of course, why we are studying this kind of thing here is because these 2 technologies is using electricity as the base one to produce hydrogen, or the solar one. And here, of course, the project 2 development is focuses in catalyst, membrane, and the integration of this technology with the solar or wind power source. This is because here in Brazil, we have a huge matrix energy based in renewable energy. So here in Brazil, we have more or less 85% of our electricity matrix is just renewable energy. And we have a huge solar power potential, which is really attractive to produce hydrogen, green hydrogen, because the production of green hydrogen depends on the primary source of energy used to produce hydrogen. And here we have a huge potential of use renewable energy to do it. So inside the project 2, which is one that I am part of, the main goal is the catalyst to hydrogen production in alkaline media. And here in LANES laboratory, This make more sense in Portuguese. The acronym is more sense in Portuguese. And I tried to here to put it in English. Is Laboratory for Nanomaterials for Sustainable Energy. And our goal is to produce the catalyst, to use this catalyst in the AEM devices. Here in the AEM device, different from the PEM, the hydrogen is produced by the reduction of water molecules. And the oxygen is produced by the oxidation of the hydroxyl ions in the alkaline medium. So this device uses the feeding of using the electrolyte, alkaline electrolyte, to produce oxygen in the anodic side of the device, and the feed of alkaline medium to produce hydrogen in the cathodic side of the device. This device, of course, can be split to explain what is the main parts of this. The first one is the bipolar plate, which is followed by the porous transport layer. Here in alkaline medium, the porous transport layer is made from nickel. It is different from PEM, where it is using mainly titanium. It increase a lot the price of the device. So we have the anode catalyst layer, the core of the cell, which is the anion chain membrane, then the cathode catalyst layer, the nickel porous transport layer. Here in the cathodic side, we can use just the gas diffusion layer based in carbon, for example, because here is not a problem, because the side of the device is negatively polarized, so it's not a huge problem. And the bipolar plate again. And the use of this device, this technology to produce hydrogen, has been studied and reported in the literature, and we have interesting data about it. For example, here, when Chen using the electrodeposition of nickel iron directly on the porous transport layer, where they use just nickel 4, they reach current density around 1.6 amperes per centimeter square in a potential cell of only 2 volts. This is really interesting because the technology is just starting. We need to stress out it. This is just starting compared with PEM, but is based on PEM technology. And here, of course, the main issues today is the AEM degradation, the membrane degradation with time. But this kind of technology have a lot of advantages compared with PEM. The first one is the bipolar plate. The bipolar plate here can be used of just stainless steel or nickel compared with titanium in PEM. And the catalyst here can be used in non-noble metals based on nickel, cobalt, iron, manganese, and so on, because they are stable in alkaline medium and are active for this kind of reaction too. But the problem is the catalyst degradation is overlooked. And why the catalyst degradation is overlooked? Because today, the main technique used to study catalyst stability is based on not just on chronopotentiometric measurements or chronoamperometric measurements. And just using this kind of technology or this kind of measurements, we can state, for example, here when the Fried and Dunn collaborator are using the ruthenium oxide as a model to show it for us, for the community, scientific community, the importance of use more sensitive techniques is that if you just see that one, you can claim that the catalyst is stable over time. But actually, they use this kind of technique coupled with the electrochemical quartz crystal microbalance. And here in blue, you can see that the catalyst is constantly dissolving over time. So the catalyst is not stable at all during the operation, even though the chronopotentiometry claiming that the catalyst is stable. So we need more sensitive techniques to verify if the catalyst is stable or not. Here, for example, they claim that the ruthenium oxide is intrinsically unstable during the operation. Intrinsically stable. And we have other kinds of examples using, for example, catalyst to hydrogen production. So here, the catalyst is negatively polarized. And even though the catalyst shows some kind of solution during the operation here, or in OCP, in open circuit potential. And the catalyst solution during the open circuit potential is at least one order of magnitude higher than the catalyst solution during the operation. So this is important. This is really important, because sometimes the industrial device just stop it to make some maintenance and things like that. So important to know what happens with the catalyst when the system is just shut down. And this is because mainly the non-noble metals in alkaline medium, this can be intrinsically stable. During the open circuit potential, for example, the catalyst can just dissolve in contact with the electrolyte. But during the reaction take place on the catalyst can just trigger the catalyst solution. So we need to know what is happening. Even if it is just a little solution, we just need to know how fast is it, what is the amount of the catalyst that is dissolved over time. We just need to know it. And how to do it here, well, how it was done there when I did my internship in Germany. There they use an elegant approach to do it, where they use a scanning flow cell here to perform the electrochemical measurements and tracking the electrolyte composition in ICP-MS. So they are using a scanning flow cell to verify a lot of catalyst spots, for example, just changing catalyst composition and things like that. And that online with that, they just tracking the catalyst degradation using a really sensitive technique, which is ICP-MS. Here they use ICP-MS because they need a technique that is in ppb or ppt levels of detection limit. So we need a sensitive technique because the catalyst degradation is in that kind of level, the ppb or ppt. So yeah, ICP-MS or electrochemical quartz crystal, all just need to develop some kind of thing like that. And here I show you an example of this one, where they did the study of the benchmark and catalyst for oxygen evolution reaction in acidic medium and in alkaline medium. Here the example that I'm showing is the ruthenium, where we can see first the contact peak solution. So this one is just the contact of the electrolyte with the catalyst surface. So when the scanning flow cell is in contact with the catalyst, we can see a healed solution of the ruthenium that stabilizes with the time. And then they just apply a potential, a step potential of 1.2 volts. And there is, again, another solution of ruthenium that stabilized. And then they perform a potential scanning. And during the potential scanning, the same potential range that there is the oxygen evolution reaction, they see a constant solution of the ruthenium that just stopped when the scanning stopped. So this means that the catalyst in this way is just dissolved over time during the operation, during the oxidation. And that was verified with other kinds of catalysts, such as iridium, ruthenium oxide, and iridium oxide. And they observed that the solution of metal is higher than the its oxide compound, as you can see here. And the solution in alkaline medium is higher than the acidic medium. Actually, the solution in alkaline medium is at least one order higher than the solution in acidic medium. This explains, in part, why this catalyst is a benchmark for PEM and water electrolyzer, but not for IAM water electrolyzer yet, at least yet. So let's focus on my research here. My research is a collaboration with the Helmholtz Institute Erlangen-Nürnberg, as I said before. This was done by me, the Dr. Tatiana Priamushko, the Dr. Serhiy Cherevko, who supervised everyone, and my supervision, my supervisor, Professor Lucia Mascado. This work was the evaluation of the activity stability relationship of non-alloy based on cobalt, nickel, iron, and phosphorus to overall water split in alkaline medium. How it was done? Because first, why to study it? Is because this kind of catalyst, this class of catalyst like metallic phosphide, is used in to overall water splitting, which means that the catalyst can be used for oxygen evolution reaction and can be used for hydrogen evolution reaction. There is a lot of reporting literature using this one for the both reaction. But actually, when this catalyst is used for oxygen evolution reaction, the active site is not the metallic phosphide, because first is produced a layer of oxide hydroxide. And this oxide hydroxide, metallic oxide hydroxide, is the active site for the oxygen evolution reaction. But for hydrogen evolution reaction, theoretically, this metallic phosphorus can be stable during the reaction, but we can see what is happening. And that kind of catalyst can be produced easily, really easily, just by electrodeposition. So this was the main goal: use something that is easily to produce it, and that this technology can be transferred to be done directly on the porous transport layer, exactly like the chain made with nickel iron in the previous slides that I showed for you. So the catalyst is electrodeposited in a galvanostatic regime, applying minus 0.2 amperes per centimeter square for 500 seconds, which produce a catalyst load around 4.1 milligrams per centimeter square, and the catalyst bath electrodeposition is just composed by the metal precursor sulfates, and as a phosphorus source is used sodium hypophosphite. Is important, this kind of information solved in this order, because this changed a little the complexion, the ions complexion formed during the solution. And how was the electrochemical protocol? This electrochemical protocol was designed to verify the stability under open circuit potential, here in the first, and during the accelerated stress test, which trying to simulate the shutdown of water electrolysis, the system of water electrolysis. So to simulate it one, we have cycles keeping the catalyst in open circuit potential for 10 minutes, and then another 10 minutes apply 100 milliampere per centimeter square. So for oxygen evolution reaction, this is plus 100 milliamperes per centimeter square, and for hydrogen evolution reaction, this is minus 100 per centimeter square. The LSV is the same. So here is the LSV, the linear sweep voltammetry, was used just to take the kinetic parameters from the catalyst before and after the accelerated stress test. So of course, for oxygen evolution reaction, the scanning is for more positive potentials, and for hydrogen evolution reaction is for more negative potentials. The electrochemical cell used to do this kind of experiments is two compartments, just to separate the reaction take place in the counter electrode from the working electrode, where is my catalyst. And the solution was taken, a liquid of the solution was taken time by time, which is this red dots here, just to see what is the electrolyte composition and what is happening with my catalyst, tracking the metal based in my catalyst, like a nickel, iron, and cobalt. The phosphorus I couldn't track. Was really hard. I tried, but I couldn't. But should be interesting to track too, the phosphorus content electrolyte. And this tracking was made by ICP-MS. So let's see what is happening. So here is showing for you the catalyst activity before and after the accelerated stress test. And here I show for you the catalyst, the overpotential during the accelerated stress test in 100 milliampere per centimeter squared. The first thing that we can see is that for hydrogen evolution reaction, there is a decreasing in the overpotential for reach 10 milliamperes per centimeter squared. So after the accelerated stress test, there is a huge decrease of the overpotential to reach 10 milliampere per centimeter squared for hydrogen evolution reaction, but it happens just in the low current density, not in the higher current density. In the higher current density, like that is one, we have other effects like the transport limitations and things like that, the bubbles on the surface and things like that, just make the analysis really hard. But the interesting thing here is that there is a huge change in the Tafa coefficient here, which means that the reaction taking place, the mechanism of the reaction changed too. So after the accelerated stress test, the mechanism of reaction changed for the hydrogen evolution reaction. But for oxygen evolution reaction, it is not observed. The Tafa coefficient here is the same, more or less, which means that the reaction mechanism is the same. And the overpotential for the reaction increase a little, but it's just a little. But the interesting thing here is, if we just look in the overpotentials during the accelerated stress test, this catalyst could be claimed as a stable. But what is happening with the metals in the electrolyte? As you can see here, in the electrolyte, mainly the solution of the catalyst, so we have a catalyst solution. The main catalyst solution happens during the open circuit potential. So in the first part of the electrochemical protocol, we can see the main solution, the main catalyst degradation. And the metal that is dissolved during this step is the cobalt. The iron and nickel is really tiny, which means that iron and nickel is stable in this kind of condition. Iron, we have just a little of iron catalyst, and this can be explained even by some kind of contamination, but not for catalyst degradation over time. But nickel is stable in this kind of one. But this doesn't happen with cobalt. Cobalt is not stable at all during the open circuit potential. But during the accelerated stress test, the behavior changed a little. For hydrogen evolution reaction, the cobalt is redeposited on the catalyst surface, and the nickel and iron is keep the same levels. So there is no dissolution. Of course, the catalyst is negatively polarized, so these metals in solution just trying to keep deposited on the catalyst surface. And it happens with the cobalt, for example. All the cobalt dissolved during the open circuit potential is just time by time redepositing on the catalyst surface. But for oxygen evolution reaction, this one, we can see that the cobalt is stabilized during the accelerated stress test, but the nickel and iron is constantly dissolving over time. But for the bulk concentration, the catalyst, the bulk concentration, this change is not significant. This was analyzed just by EDS analysis, but the EDS analysis is a bulk concentration, not surface technique. It is not a surface sensitive technique to do it. So let's go to a surface technique to see what is happening. The surface is in the near surface, the underneath surface. Let's start with the depth profile XPS analysis here of the cobalt, cobalt 2P. As you can see here in the cobalt concentration from the surface, here in 0, from the underneath surface, for the near surface, we can see that behavior is more or less the same for the three situations, which is the as electrodeposited. So here is the catalyst just electrodeposited without use. For hydrogen evolution reaction in blue, and for oxygen evolution reaction in red here. The catalyst behaviors is more or less similar for both. We can see that the surface is composed by hydroxides, more part of oxide metal. So here we have a lot of cobalt oxide. But underneath surface, we have cobalt, metallic cobalt here. So this peak and this peak is characteristic for metallic cobalt, and these peaks and this one is characteristic for cobalt oxide. And this happens with the hydrogen, after hydrogen evolution reaction too. We can see some kind of cobalt oxide, even underneath surface, but more deeper, we can see the metallic form. But for oxygen evolution reaction, we can see peaks characteristic, the shift characteristic of these peaks and behavior of high valence cobalt here. So here we can see that these peaks actually are responsible for high cobalt valence. And this high cobalt valence is stable in alkaline media. So this explains why during the oxygen evolution reaction, actually the cobalt concentration, the electrolyte is kept, is stable, it doesn't increase. It's because as soon as this higher valence cobalt oxide is produced, the catalyst surface is passivated and is protected. So there is no more catalyst solution, even with these steps of open circuit potential. For oxygen, we can see that there is a surface covered with oxide, hydroxide metals. This peak is for hydroxide, so it just corroborate the analysis of cobalt, that the surface is covered with hydroxides, even for the catalyst as electrodeposited. But for hydrogen evolution reaction and for oxygen evolution reaction, the underneath of the catalyst, we have the oxide-hydroxide. So we have both species here, the hydroxide and the oxide, which means that underneath surface we have an oxide-hydroxide layer of these metals. The behavior of the oxygen concentration in the surface and after surfacing is more or less what it was expected. There is more oxygen in the surface than the underneath, and deeper in the catalyst surface. And for nickel, we have a little different behavior of the nickel concentration in the surface and the underneath surface. For oxygen evolution reaction, we almost don't have nickel. Almost don't have. It's just a little of nickel on surface. But for hydrogen evolution reaction, the nickel on surface is more or less the same that as electrodeposited. So the negatively polarizing of the catalyst just protect the nickel solution. But for oxygen evolution reaction, after the nickel is dissolved during the reaction of oxygen evolution, and not during the open circuit potential. So the cobalt is dissolved since the open circuit potential step, since the first step, but the nickel is dissolved just during the oxygen evolution reaction. And we can see the same. The surface is composed by oxides, nickel oxides, and the underneath we can see the peaks characteristic of the metallic forms for the hydrogen evolution reaction and even for oxygen evolution reaction. So even after 24 hours of cycles applying 100 milliampere per centimeter square, the catalyst film is not completely oxidized. we have some kind of metallic forms there. And for phosphorus, they show that phosphorus is not stable at all. So just putting the catalyst on the electrolyte and the surface, the phosphorus surface is completely dissolved. Even under the surface, the phosphorus is completely dissolved. We don't have any phosphorus on the surface and even in closed surface. This is a little trick because we have the total etch time, but we don't have the layer of the etching time. What was the thick of catalyst that was etching during this time? But this illustrates very well what is happening with the catalyst underneath. So we don't have phosphorus on surface for hydrogen evolution reaction and for oxygen evolution reaction, which means that it's just putting the catalyst inside the alkaline medium and the phosphide is just solved. But underneath we have. So underneath we can see the characteristic peaks, the binding energy for the metallic phosphide bonds here, for the hydrogen the same, and for oxygen evolution reaction the same, and for the phosphates, the bind and the energy bind of the phosphorus oxide here for the oxide, for oxygen evolution reaction, for hydrogen evolution reaction, and even for the catalyst as let's deposited. So let's concentrate what is happening with the catalyst just in the open circuit potential, because here we have the huge solution of cobalt in the catalyst. And here you can see that the catalyst solution, the cobalt solution, is directly proportional to the alkaline concentration of KOH in the electrolyte. So the higher the KOH concentration, the higher the cobalt solution, which means that working with this kind of catalyst containing a lot of cobalt in conventional electrolyzers or alkaline electrolyzers is not a good idea, because they use 6 molar of KOH, and 6 molar of KOH, as you can see here, is the catalyst solution is really higher compared with the other ones. But in 1 molar KOH, the same behavior. The catalyst solution is dissolved linearly over time. So it's just keeping the catalyst in solution, and someday the catalyst is just completely dissolved. If we use more diluted solution, we can see a lower catalyst solution, a lower cobalt solution. For iron and nickel, we just see the nickel solution in pure water, which means that the use of nickel to anion exchange membrane water electrolyte using purified water is not a good idea, too, because we just can't treat the nickel solution. So we need to put some kind of alkaline in the medium just to keep the nickel stable over time. But for iron, we can't see any kind of iron in the electrolyte during the open circuit potential. And as you can see here, we just verify what happens with this catalyst when we are trying to simulate the environment of the reaction, purging the system with hydrogen or purging the system with oxygen. Let's say that during the operation of the water electrolyzer, the cathodic side, we can just use the hydrogen to purge the system, and in the anodic side of the electrolyzer, we can use the oxygen to purge the anodic side to keep the environment the same, the environment that is producing during the reaction. So, as you can see here, if we use this gas to purge the system, for hydrogen or oxygen purging, the cobalt solution is really lower compared with argon. So the most part of the reports in the literature just using nitrogen gas to purge the system of argon gas. But actually, this kind of gas is not used in the water electrolyzer. It's not used. What is produced in the water electrolyzer is hydrogen or oxygen. No, actually both of this gas. So what happens with the catalyst when the environment is kept like that? We can see here that actually, even in open circuit potential, if we purge the system with these two gases, the cobalt solution decrease a lot, decrease 5 or 6 times in open circuit potential. And this happens because with the hydrogen evolution, with the hydrogen purging, the potential of the electrode is kept lower than the hydrogen evolution reaction, the potential, the thermodynamic potential for hydrogen evolution reaction, which means that probably the purging with hydrogen keep the environment like a reducing environment to protect the metallic oxidation. And with oxygen evolution reaction, actually, the potential cell here, as we can see here, is higher and produce the high valence oxides, which means that the production of the high valence oxides can just passivate the surface catalyst and protect catalyst of further dissolution. And this happens when we just are trying to change the oxygen concentration in the purging gas. If we use none of oxygen in the purging gas, like here in the black line, we can see a linearly solution of cobalt over time, which means that the cobalt is just dissolving over time. But we've just put a little of oxygen in this kind of purging gas, like a 6% more or less. Here in the red line, red dot line, we can see that behavior is different. We have a huge solution starting, but after 1 hour, more or less, the catalyst solution just is trending to stop, which means that with time, the catalyst produces the passive layer and protect the cobalt solution. So we have actually a competition between the dissolution of cobalt, because the cobalt oxide is not stable in alkaline medium due to this reaction, and the passivation of the cobalt oxide to producing the high valence cobalt oxide. And this competition means that if we have a lot of oxygen in the purging gas, we can protect the catalyst solution. So, what is happening with the catalyst? The cobalt solution mainly occurs during the open circuit potential due to this instability of oxide, of cobalt oxide. In alkaline medium, the cobalt oxide is just dissolved by the production of the cobaltite. The nickel and iron can be dissolved because the instability of the oxide, the metallic oxide, the iron and nickel oxide, to producing the oxide hydroxide, that is the active sites for the oxygen evolution reaction. But when this catalyst is just keeping an open circuit potential, this oxide hydroxide is not stable, so this just produce the oxide layer, and this movement, this change in the structure that promote the catalyst solution. So that is why in the catalyst for oxygen evolution reaction, we can see the nickel solution. There is no nickel on surface, but for the S electrodeposited and for hydrogen evolution reaction, we can see actually nickel. Phosphorus is not stable at all. So phosphorus just put the catalyst in electrolyte, and the electrolyte and the phosphorus on surface is just dissolved. With argon purging in open circuit potential, which promote the catalyst solution actually, is the impurity of oxygen inside the gas. This impurity of oxygen just produce the cobalt oxide, and the cobalt oxide is again dissolved by the production of the cobaltite. If we have oxygen purging during the open circuit potential or hydrogen purging, we can just passivate, protect the catalyst, passivating the catalyst surface when we using oxygen purging by production of high valence and cobalt oxides, or protect the catalyst, keeping the environment like a reduced environment to protect the production of the metal oxide. So if we just avoid the production of the metal oxide, we can avoid the catalyst solution. I would like to thank everyone for your attention, in special the founding agents, FAPESP, CNPq, CAPS, and the Shell to believe in us, and the DAD from the Germany for the support there. So here is my email and the email of the Dr. Serhiy Cherevko, and please feel free to write for us. Thank you, everyone. And here is just a photograph of the group of LANES at LANES group. Thank you.
Okay. Thank you very much for the very wonderful and then insightful talk. And then starting from your career, moving to the program, and then your scientific contribution. And now is time for questions. We have a lot of participants here at the moment. We reached 63. Now we are 61. Just raise your hands, and then we can start the discussion to move further. Lucas Freitas.
Hello, Giovanni. Thank you. Can you hear me?
Yes, I can.
Okay, thank you for the talk. I'd like to ask, you said that you use a nickel, cobalt, iron, and phosphorus layer, right, for the catalysis. And I wonder, do you use this combination because the elements, the first three actually, have a similar electronic structure, or is it due to a geometric effect? What makes this material good for catalysis?
All right. I use the nickel cobalt because they have electronic similarities for the study of catalysts. And the iron, I put like an impurity in the system. It's because iron is really tricky, really, really tricky. There is iron for everything, you see? So it's really hard. You use really purified salts, precursors, and keep all the system since the electrodeposition and then for the characterization without iron. It's really hard, really hard. And so on. I just think, okay, let's go for put some kind of iron in the catalyst, just simulate to the impurities, and yeah, is that. But nickel and cobalt is because of the electronic characteristic.
Good, thank you. And if I may, I have another question. I wonder if you can tweak, if you can tune the portion of nickel and cobalt in order to target a specific reaction, like HER or OER. Is it true, or?
Yeah, I did. There is a lot of work with the optimization of catalyst here, and I try to change the metallic precursors in solution during the electrodeposition, and use these precursors for hydrogen and oxygen evolution reaction. Actually, for example, if we are just using cobalt phosphide for hydrogen evolution reaction, he has a similar behavior of these three metal alloys. The nickel phosphide is not so good like a cobalt phosphide, but the thing here is if I use the nickel and cobalt phosphide, I can keep the catalytic activity more time than if I use just cobalt phosphide. You see?
Yes. So, thank you very much, Giovanni.
Okay, thank you for the question. Now we have further questions. Just raise your hand. Okay, I think I have to part of my. Okay,
I
Ana
have questions.
Nogueira.
Yes. Hello, Giovanni.
Hello, Ana. How
Hello.
are you?
Congratulations for this amazing talk and results.
Thank you very much.
So I'm going to ask you a question that probably you're going to see the same questions for the other postdocs that are going to present here at CINE Talks. As you know, our center is sponsored by a company that is, of course, is very interested in fundamental, is interested in answering some fundamental questions, but of course, it's much motivated by the market, right? So my question to you is like, how is what's going to be your next big further step? I mean, you're developing beautiful research. We know that, publishing amazing papers in high-impact journals. But you know that the company wants more. You want to see something at the end, okay, of this pipeline. You want to see like maybe a product at the end.
Yeah.
And CINE is really, really involved in training the postdocs. You know, we had this one-day event here, I think it was in May, when they brought this company, Scala Lab. This kind of venture builder is a company that is, they know how to speed up startups. So startups is something that really all the postdocs, maybe not all of them, because some of them are really considering to pursuing the academic research. I don't know if it's your intention, but others are very interested in build startups and everything. But we cannot forget that Shell is our main sponsor, and at the end of the pipeline, the company really wants to see a product in the market. So this is my questions to you. It's going to be, I think, for the next postdoc. So how you are considering this? How are you working with this idea? Do you see possibilities in the work that you're doing in São Carlos, the possibility to have like a product, or even considering the possibility to open a startup? So tell me more about it.
Yeah, of course. The idea is to, in my case, my idea is to study the catalyst for IAM electrolyzer. So it's more or less like, I can't compete with PEM electrolyzer, see? PEM electrolyzer is a matrix technology, so it's like, yeah, there is huge companies working on that, so it's really hard to compete with this one. But for AEM electrolyzers, this is just starting. That can be a really great step for us here. So it's like my focus is in catalyst for this one, for this technology. And as we are working here, it's more or less like there is a part of the team focus on the catalyst for the AEM water electrolyzer, which is just a piece of the technology. There is a part of the team focus on the membrane, and there is a part of the team focus on the how to deposition of this catalyst on the membrane to produce really AEM technology, you see? But in your case, in my case, I'm more interested in how to use the electrodeposition knowledge that I have to produce the catalyst directly on the porous transport layer and use it like a technology through AEM, you see? So it's like, if I can't do it, the other part of the let's say, the future thinking about the companies and things like that is how to put it with a stable membrane and produce really AEM electrolyte. You see?
Thank you, Giovanni. And for you and the other postdocs that are attending this talk, it's really important for you to know that we really, CINE Hub, we really encourage you and the other postdocs to consider the possibility of a business, to consider a possibility to see a business model in what we are doing. And also, we really want to support these ideas. So just be aware that I think it's going to be, we haven't decided not yet the date for the week, but we are going to have another school of entrepreneurship where this company that we are still discussing the contract with them, Scalab, they are venture builders. So the idea is to look at some of the projects, finished projects at the moment. And this company is going to select some of the projects to actually to speed up the process for establishing startups and so on, how we can submit a PP project. So just for you and for those, we are really encourage like the postdocs, those that really want to pursue the career in the business that we are here. I think Cauê just raised his hands.
Yes, the next one. Next question.
Rafael.
Yes. Okay. Thanks, Ana. Next question by Professor Cauê Ribeiro.
Well, thank you. Just connecting with the question that Ana has given. That's really remarkable, Dyovani. The nice quality of our results, your scientific results are quite impressive. But I still have a question that I was thinking on that, specifically on the aspect of applicability of electrodeposition, because you said that electrodeposition is something interesting to make the catalyst directly on the membranes, directly on the systems, but it is still limited to small sizes. How can we scale up this, thinking that the electrodes, most of them, they have sizes of, most of the commercial electrodes, they are around 100 square centimeters at least. Some of them are much bigger than this, but just thinking on AAM, prospective technology for AAM, we are thinking on something like a 10 to 10 at least. But this is not, this doesn't seem to me as doable, at least in the systems that we have. How can we fight against this problem? And the second question I have is about your utilization of oxygen to stabilize the cobalt lixiviation in your system. So I didn't understand this clear, if you are doing this on the anodic or cathodic part.
No, no, see, the oxygen is the purging with the gas was used just to simulate what happens during the open circuit potential.
Okay, so this is
before,
just the cathodic part.
Yeah, it's before any kind of reaction.
Perfect. Because on cathodic part that might be really dangerous. But anyway, let's keep on the discussion about the scale up.
All right, let's talk about the electrodeposition to scale up. That is because you are thinking the electrodeposition just in the classical way, just using the a vessel, and the electrodes put inside this vessel and did the electrodeposition. So it's like, okay, if I use porous electrodes like a nickel foil or nickel felt or other kinds of porous electrodes, we have a huge problem with this kind of approach to electrodeposition because, of course, we can't guarantee the deposition inside the porous, because the deposition will be just on the surface and blocking the porous, and there is no deposition inside the porous anymore. So, but we can use another kinds of approach to do the electrodeposition inside the porous of this electrode. For example, we can use an approach like a flow electrolyte that pass through the electrodes, porous electrodes, to do the electrodeposition. How to perform this in a large scale, for example, we are studying just electrodes like a 1 per 1 centimeter square. But if I use electrodes like I don't know, 1 meter for 1 meter, so that kind is a really challenging. And we need to study how to promote the same environment of transport ions and precursors during the electrodeposition equivalent for all the surface of the catalyst. This is really challenging. Yeah, I can say you that I have some ideas to do it in scale, but of course we need to try and to prove that this works, you see. In my idea, the use of flow systems with different feeding parts, like I have a huge electrode, but instead of I have just one channel for flow, I have a lot of channels for flow to keep the same concentration passing through the porous electrode all the time in the same, like in the 1 centimeter square electrode, you see? But we need to prove that one. It's not just a, yeah, it's a really challenge. Just produce this one.
Have you tested, for instance, doing this directly on the ionomers instead of doing this on the membranes? Because if you do this on the ionomers, you can separate this as a powder and use this as an ink directly. So it might be possible in that way, because in that sense, you don't need to produce 1 meter per 1 meter, 1 square meter electrode directly, but we can produce the particles directly attached to an ionomer, and after that, making the deposition in the membrane.
But like in the ionomer, I need to work with the powder, you see? The production of powder, all right. But the beautiful of electrode deposition is that there's a really simple way to produce this one. Even if I am using just something like a microporous flow system, like that I was saying before, I can use the same electrolyte for 1,000 hours, you see? And it's just like, it's the same that the electroplating, but using the flow system and forcing the electrolyte passing through the electrode, the porous electrode. So it's a totally different approach. But yeah, for using powder is easy, but the synthesis of the powder is the tricky, you see?
Okay, thank you. We can discuss this further.
Thanks, Kyle, for the question for Giovanni. Now we have a last question by Rafael Nagal.
Thank you, Giovanni, for. Can you hear me?
Yes, I can.
Okay, thank you very much for a nice talk, and also for your efforts to assemble the electrolyzers for us. That we are very anxious to start the experiments. And so my questions are a little bit more fundamental. Based on your experiments, it seems that it's better to start with the spinel oxides, right?
Yes.
Because it's stable, and I believe that the performance is even better too.
Yeah.
So my question is, why do you think it's a chemical explanation? Why do you think this spinel oxide is more stable than the other oxides? I mean, saying that because we have the same phenomena using nitrate reduction with these spinel oxides in the cathodic reaction. It's very stable. We also did some this accelerate stress testing, and the structure is very stable. It doesn't change at all. We change the potential. So I was wondering if you have a good explanation for that, if you know why this is so stable, even in very harsh conditions like 6 molar of sodium hydroxide.
All right. There is some kind of there is some literatures that claim that the differences between the metallic coordination, you see, is like they explain that in spinel structure, the metallic coordination with the oxygen around him is like more protective than the oxide. But it's not so simple, in my opinion. I think that there is more like I think that the high valence of this metal centers protects the metallic center from the hydroxide attack, because the oxygen atoms around him coordinate with him is more bounded. You see, is more like the bonding, the strength of the bonding is higher. So I think that it's not so easy for hydroxyl ions attack these metallic centers in the high valence metallic. It's not just a coordination, but the coordination is like a result of that, right? So I think that is like this could be like the strength of the oxygen bonding with the metallic center.
All right. So and the performances are better when you have.
Yeah, the performance is better.
Okay. Thank you.
But
Thank you.
Performance is just for it's not for the catalytic activity. It's just for the dissolution profile. You see.
Oh, okay.
It's because the production of these high valence, these spinel compounds, is is produced during the reaction. So if I have oxygen evolution reaction, I have the production of these spinels. It's like that. But if in open circuit potential, I can produce these spinels just for oxygen purging without forcing the reaction, applying potential and things like that.
Okay, nice. Thank you very much.
Okay, I would like to thank you, all the participants, and those ones that make the questions, point out the challenges. And then for last, I would like to thank Dyovani Coelho for the very nice talk and insightful discussions. And then we're going in 2 weeks, we're going to have a next talk. We're going to announce it just in a few days for everyone to be aware and to set up on your agenda. Okay, thanks a lot for everyone. We try to keep on time, okay, for everyone. Thanks, Dyovani. Thanks for everyone. Thanks for Camila Pedroso for all the organization.
Thank you.
Okay, thanks. Great.